In this lecture, we're going to take a look at aggregate and how it plays a role in the design of our road surface. Topics to be covered, we're going to look at aggregate sources, aggregate terms and types, aggregate strength, the properties of aggregate, specifications that we're going to look at, sampling and testing that we may have to do, blending aggregates, and we're going to look at test procedures that we're going to use in order to get a good understanding of how the aggregate is going to work with the design parameters that we have established. Let's start by taking a look at aggregate itself. And aggregate are granular mineral materials used alone or with various types of cementing materials to form concretes as road bases, backfill, and a host of other uses that are required to stable or have a stable foundation created for the supporting structure that we're going to be placing on it. Aggregates are mineral particles of a soil specifically related to the granular soil groups like gravel, sand, and silt. And we took a look at this already with our sieve analysis tests and things like that that are going to break up the samples that we have. Typical use of aggregate or Portland cement. We get asphalt concrete, we get asphalt surfaces, road bases and sub bases. We're going to use trench backfill materials and for fill under floor slabs and things along these lines. The required aggregate blend is subjected to the proposed use of its need. And again, this comes from the design professionals who are going to spec out what requirements they're looking for in order to create a good base that our structure is going to sit on top of. We have to keep in mind that there are basic properties and tests used to evaluate these properties apply to most uses of aggregate within the construction industry. So it's pretty much a standard that we're going to follow and get a good understanding of how these particles are going to act and form together during our compaction and things along these lines. What are the sources, or what are some of the sources that we can get our aggregate from? There are natural sand or gravel deposits. Of course, we have crushed rock. We have slag and mine refuge. We get rubble and refuge. We get artificial and processed materials that we could have. Pulverized concrete and asphalt pavements. Other recycled and waste materials that we could use. And of course, the first two sources supply the bulk of the aggregate used within the construction industry. So we're looking at the natural sand or gravel deposits or crushed rock that we may have. Natural sand and gravel deposits normally come from sand and gravel pits that have naturally sorted the sand and gravel soils to eliminate most of the silt or clay sizes that are also part of that deposit. Then deposit these soils in glacier formations, river deposits, and beaches of current and previous lakes and seas that we have. Sand and gravel pit development starts with stripping of the topsoil and vegetation from the surface layer that we have. Once this is completed, excavation of the mineral begins and loose materials are moved from front-end loaders or through the use of front-end loaders and crushed depending on its overall size and specifications that we need. Larger size aggregate is broken down to desired sizes, and crushed gravel is considered high quality aggregate and are usually processed through wash plants, which cleans the dust off the aggregate by removing the silt and clay materials or particles that we have. The type of material mined depends on the bedrock source that falls into three categories: igneous, sedimentary, and metamorphic. And of course, igneous rocks, original bedrock formed from the cooling of molten material that we have over time. Coarse-grained igneous rock, granite, cooled slowly. Fine-grained igneous rocks, trap rock, cooled rapidly. Sedimentary rocks, as we can see here in our picture, solidification of chemical or mineral sediments deposits under ancient seas. We get layers or layered since original material was deposited in this manner. Examples of these types of rocks are limestone, shale, sandstone, gypsum, clay, quartz, gravel, and of course, sand materials. Metamorphic rocks are igneous or sedimentary rocks that have been metamorphosed due to intense heat and pressure. Examples of metamorphic rocks are slate, scale, marble, limestone, sandstone, and granite. Igneous and metamorphic rocks, if we take a look at them, are rocks that are very hard to make an excellent source for aggregate materials. Limestone and dolomite are common sedimentary rocks that are softer than igneous rocks but are acceptable for aggregate use. Shale is primarily composed of clay grains and is weak and disintegrates easily. Chert is another sedimentary rock that also disintegrates easily. So here we have a picture of a quarry pit development. So as mentioned before, top layer is stripped off, we get down and we start to excavate the area for the materials that we need. So aggregate that comes from bedrock materials are often developed or have come from a quarry of some sort. The process starts by opening and stripping of the face of the quarry and then blasting of rock with dynamite into sizes that can be transported. Crushing of the rock into the required aggregate sizes is completed by the rock crushers that we have on site. If we take a look at the slag and mine refuse, slag is a waste material resulting from the treatment of ore to produce iron, steel, nickel, or other materials. Blast furnace slag from iron mills is a common aggregate that can be used on different types of projects and job sites. Mine tailings can also be used as an aggregate. Rubble and refuse as aggregate materials. Recycling of pulverized concrete from structures. I think I mentioned this before. We call it R-blend. Recycled asphalt pavements in base courses. Recycled rubber and crushed glass in base courses. Aggregate terms and types that we would have. Of course, we have fine aggregate. Aggregate particles mainly between the 4.75 millimeter and the 75 micromillimeter or meter sieve or sieve size that we would have. Coarse aggregate, we're looking at aggregate particles mainly larger than the 4.75 sieve size. We get the pit run, aggregate from a sand or gravel pit with no processing. We get crushed gravel. It's a pit gravel or sand that has been put through a crusher either to break up the rounded gravel particles into smaller particles or to produce rougher surfaces that we may need. Crushed rock, aggregate from the crushing of bedrock. All particles are angular and not round as in gravel. Screening, we get chips, dust, powder that are produced from the crushing process that we have. We get concrete sands, sand that has been washed and removed dust and fines that we may have. And of course, we get the fines, silt clay or dust particles smaller than that 75 or number 200 sieve size, usually due to the undesirable impurities that are in the aggregate materials that we have. Nominal size, this is the term that is normally used to describe and specify aggregate as needed or required. It is not economical to have 100% of the particles of an aggregate be within a specific range or size that we have. Again, this is all specifications spelled out by the design professionals. Reduce as much rejected as possible from the pit in order to efficiently use the material resources of a pit that we are excavating. And usually 5 to 10% of the aggregate particles can be allowed to be larger or smaller than the specs that we have. And this makes sense because it would be almost impossible to crush aggregate down to a specific size based on natural and environmental conditions that we have. So design professionals may spec out 3/4 bluestone for a project with the intent or understanding that the aggregate material will fall somewhere within this range. Of course, aggregates will fall within the 19 to 4.75 nominal aggregate range that we would have. And of course, with fines being 4.75 millimeter nominal aggregate sizes. Clear aggregate, a single grain coarse aggregate is called clear. Most of the particles are between the specified maximum size and a minimum size, which is again defined as 1/2 of the maximum. For example, a 19 millimeter clear aggregate will have 100% smaller than 25 millimeters, 90 to 100% smaller than the 19 millimeters, and 0 to 10% smaller than 9.5 millimeters. We look at the strength of the aggregate. Aggregate are used mainly as layers of particles to distribute imposed loads over the surface of a soil or as a material used within the concrete mixes. So again, we talked about compaction. We're looking at that strength. We want to get it as strong as we can to get those particles to move together. The strength of the individual aggregate particles themselves, not a controlling factor in how they are used within a construction project. Cubical and round-shaped particles of gravel or stone are usually much stronger than the concrete mix itself that is designed to support a structure. And this is due to the ability of the layered aggregates to carry more load without the soil particles sliding over each other, which become the important aspect of their strength properties. Let's take a look at some of the aggregate properties that we want to consider when we make our selections and our design parameters that we're going to guide us in the effort to support the structure that we're going to place on it. So we want the following. So we get the gradation. We get the relative density, specific gravity, and absorption. We already looked at this. Hardness, the resistance to wear. Durability, the resistance to weathering. The shape and surface texture. We want to look at the deleterious substances that we have and the crushing strength that we have of the properties of our aggregate. And also we want to know if it's soft and lightweight particles that are making up this aggregate material that we're going to use. Let's take a look at the gradation factor in our road design. It's the most common test performed on aggregate based on the grain size analysis and distribution. With highway and roadway bases, concrete and asphalt surface mixes, specifications require strong mixes with dense properties. We want to make sure the road surface is going to last for the time frame that it's been designed for. High density mixtures are important in terms of density and asphalt cement required. Asphalt must coat each particle and fill in most of the void spaces that we have. And with these specifications, we are trying to eliminate the overextended use of aggregate to fill in void spaces, which in the end will reduce the asphalt cost and, of course, weaken the roadway surface. Ensure the maximum density and strength using the maximum density curve. And we continue to look at gradation here. It's the strength and resistance to shear failure of road bases and pavements is increased greatly if the mixture is dense or a densely graded material. The larger particles are in contact with each other, developing frictional resistances to shearing failure that may happen. Particles are tightly bound or bond together due to the interlocking effort of the smaller particles. So again, we talked about this in compaction. We're trying to get those particles to move back together to increase. Other factors that we want to consider with gradation, we want to limit the amount of fines that are in our mixed material. Silt and clay particles are relatively weak forces that we're going to deal with. Dust or larger aggregates will interface with the aggregate asphalt bond that we have. Excessive fines in a base or sub-base may lead to drainage or frost heaving problems that we may have. Excessive fines, of course, smaller aggregates results in weak structures because larger particles are not in contact with each other. Of course, the strength is reduced. Smaller particles result in weaker mixes. Therefore, it becomes very important to manage the percentage of fines within our total or overall aggregate mix. When we look at gradation, we want to look at the washed sieve analysis. And it's important to determine the amount passing through that 75 sieve size that we have. Sample is dried and washed, and the washed water is poured out over the 75 micrometer sieve that we have. The material retained is returned to the sample for the sieve analysis. The total amount passing, again, our 75 micrometer is equal to the amount lost in the washing, and the percentage passing, again, that sieve size. Relative density, we kind of talked about this already, specific gravity and absorption. So the relative density, or the specific gravity, and the absorption of the aggregates are important properties, especially in asphalt cement mixes when supporting highway and road surfaces. In the mix designs, it is important to measure accurately the volumes occupied by the aggregate and any water that may have seeped into the pores in the particles. Therefore, voids must be considered in the aggregate within the mix and design process. Saturated surface dry. All permeable pores are filled with water, and we look at the bulk volume, or the volume net, plus the volume of the absorbed water that we have. So if we look at some test equipment here, so we got an SS detect apparatus for determining, of course, the SSD of the aggregate. We also look at the Los Angeles abrasion apparatus, the Duval apparatus that we could use. Let's take a look at the aggregate hardness, of course, the resistance to wear. It is important that aggregate for pavement surfaces not become rounded or polished due to the simple fact that they will reduce skid resistance. Load cycles in the pavement structure tend to break aggregate or fines down, resulting in changes to the gradation or the finer, which will result in reductions of the strength of the overall pavement surface structure. Broken aggregate are not cemented into the pavement structure, which again will reduce the strength of the road surface or the highway surface that we have. Resistance to degradation during the mixing, transportation, placing, and compacting is important because soft particles may break, changing the gradation of the overall mix design. The hardness test, of course, we have the Los Angeles abrasion test. Test measures the hardness of the aggregates. The Duval apparatus aggregate impact value test, polished stone value test that we could look at or use. Aggregate durability, resistance to degradation due to cycle of wetting and drying, heating and cooling, and of course freezing and thawing. Freezing and thawing play a major role in the road surface survival, and we see this a lot, especially in areas that get cold and we have plowing, and it really tears up the surface. Pore spaces in the aggregate are often saturated with fluid and on freezing expand. And repeated cycles of this event can cause the aggregate to break and cause failures. And of course, we see this, simple thing of just putting ice or water into the freezer in an ice tray, and we see how the ice expands in the tray. So we're getting that same effect here, except in this, it gets into the particles. As it freezes, it causes the particles to break loose. Sedimentary rocks are vulnerable due to the plane of weakness between binding layers that we have. Soundness test, field performance, absorption value that we could look at. Aggregate particle shape and the surface texture that we're dealing with provides bonding capabilities with asphalt cement. Soil particles with rough fractured faces allow for a better bond to take place with the asphalt cement materials than rounded, more smooth particles would provide. Provides the resistance to one particle sliding over another within the mix. Thin, flat, long aggregate particles break easier than cubicle-shaped particles. Specifications restrict the percentage of long, thin particles and requires aggregate particles to have at least one fractured face. Deleterious surfaces or substances, harmful or injurious materials, including various types of weak or low quality particles of coatings found on the surface of the aggregate. Of course, we're looking at dust, materials passing that 75 sieve size, clay lumps, scale, coal particles, friable particles, chert, weak in terms of freezing and thawing. These substances affect the bond between cements and aggregates and break easily. Petrographic analysis rates aggregate particles as excellent, good, fair, or poor. Sand equivalency test is often required to measure the amount of fine dust or clay-like materials on aggregate particles that we have. Aggregate crushing strength. Crushing strength is a compressive load that an aggregate particle can handle or carry before it will break. Relatively unimportant for most aggregate strength because it is usually higher than the strength of the asphalt mixture or the overall asphalt mixture. Soft and lightweight particles. Soft particles may be unsuitable where they may be exposed to abrasive conditions in construction projects related to concrete floor slabs or, of course, gravel road surfaces. Lightweight materials in the forms of coal or chert may be weak or porous and result in poor surfaces or, of course, pavement. Chemical stability refers to specific problems due to the chemical composition of the aggregate material that we're using or dealing with. Aggregate susceptible to stripping may lead to disintegration of the asphalt surface. Reactive aggregates may cause the breakup of the Portland cement concretes that we're using. Specifications. Specifications by Highway Department takes into account the aggregate particles that have been discussed. Requirements for aggregate to be used in bases and sub-bases differ from the aggregates being used within the asphalt mixes. Specifications include local experience along with the availability of the aggregate materials for the project that is being undertaken. Sampling and testing. The characterization of the aggregate source depends on how representative the samples are from the taken source of the aggregate supply. The aggregate size is normally specified depending on the aggregate needs and the requirements. Aggregate samples should be obtained from the final product if possible after all the steps in processing and transportation have been completed. And again, mentioned it before in a Module 2 lecture, we're looking to get a quarry that's close to our site so we can reduce the cost of transportation and so on. So it's important that we take these into consideration as we move from site to site around the country and so on. Samples taken from the production or discharge should be taken at various times and across the entire cross section of the discharge and combined to form one sample. Sampling from stockpiles requires care due to the possible segregation of the material, and 3 samples should be taken, one from the top third, the middle third, and the bottom third, and combined. Sample tubes for fine aggregate stockpiles should be used with 5 tube samples obtained or combined. Samples taken from a truck or railway car should be done from a cross-sectional trench, 3 combined again to form one sample. Combined samples should be done with equal size component samples. Randomness should be used to determine location or time to eliminate personal bias. Ensure proper identification of the sample. Samples should be properly secured. Samples tested in the lab must be representative of the samples delivered to the lab. Sample splitting. Testing aggregates composed of significant amounts of both coarse and fine aggregates. The sample must be split on the 4.75 sieve and the 2 fractions sieved separately. If not, the amount of sample on the fine sieves may be too great for effective sieving. Blending aggregates. As we all know, it is sometimes hard to meet the gradation requirements for the asphalt or the concrete mixes, and blending 2 or more aggregate types is required to meet the design parameters or specifications established by the design professionals. Readily available charts and diagrams can be used to accomplish this task, but the trial and error method is simpler and sometimes faster to complete than looking at blend mixes on a chart. This concludes the Module 3 lecture on aggregates. Again, please make sure you take a look at the PowerPoint presentations and take a look at the examples that are provided to assist you with any homework requirements.